So welcome to this series of lecture which is called Modern Tools for Rational Points on Curves over Finite Fields. I'm Christophe Ritzenthaler, and together with Stefano Marsiglia and Anna Somoza, we are going to introduce you to the wonderful world of curves over finite fields and their rational points. So I guess, like for every long quest, one needs a purpose. One needs like a goal, a Graal. So what is going to be our Graal? I mean, I'm going to write it on the blackboard, and probably it's not going to tell you so much right now. But the questions that eventually at the end we really want to address is the following. Is there a genus 5 curve over F47 with 113 rational points? Okay, this is a very specific question, right? And I think before even starting to see, I mean, if we want to get involved in the long process of studying all the materials we need to look at these questions, I mean, we have to be a bit skeptical. Is that a good question? And how do you distinguish a good question, mathematically speaking? Well, let's try to see what is a good question in mathematics. So what is a good question? Well, first, it is a question which is not solved yet. Right? B, well, a good thing for a good question is that there are more people interested. Three, I think a good question is that when you try to solve it, you learn many things on the way. So you learn things, materials that you can use for other purposes in math. Well, and maybe D, it can be solved. All right, so let's see, I mean, if this question fulfills these 4 requirements. So for the first question, it is not solved. So, of course, I mean, the difficulty right now for you is that you might not know what is a genus 5 curve. I mean, I guess you know what is a finite field, and also maybe rational points. So genus 5, you should really understand it like the genus as a measure of complexity. So where does 5 stand? 5 is already like a quite medium hard complexity. Okay? You will see, I mean, we will see together at some point that right now people are even stuck in general with genus 3 curves. So I mean, genus 5 it might be quite hard. Rational points, I mean, this is something you can guess, I mean, because maybe you're already familiar like with other kind of situation, like, well, I mean, the most famous one is maybe Fermat's last theorem. You know, I mean, you have probably seen it when you look at this equation. And you say that n is going to be an integer greater than 2. And you want to solve it not with any complex number or on any real number, but you want this x, y, and z to satisfy some constraints. And in particular, here for Fermat's last theorem, we ask x, y, and z to be integers. And so you know that the famous result is that when n is greater than 2, the only solutions are trivial ones like 0, 0, 0, plus or minus 1, 0, plus or minus 1, 0, plus or minus 1, plus or minus 1. And also you can have, if n is odd, you could have plus or minus 1, 1 or plus 1, and 0. I think with that I have them all. So these are rational solutions. And of course, over finite fields, we are going to take the coordinates to be inside these fields F47. But as you don't know what is a genus 5, I mean, how are we going to see if it is an open problem or not? For this, let's go together and see this page, which is called manypoints.org.
All right, so here we are on this web page, manypoints.org. So as you can see on this web page, you have prime numbers up to 100 and some of their powers. These prime numbers and their powers, of course, represent the order of a finite field. So a finite field F5, F7, F49, and so on and so on. So let's click on one of these values, let's say 13. So now you see that for this value 13 up to genus 50, you have some numbers which represent number of rational points. So when there is only one number, like here for genus 1, this means that there is one genus 1 curve with 21 rational points over F13, and this is the maximals that you can hope for. Sometimes you have only one upper bound, so which means that the best that you could hope for is this number. So for genus 23, you could hope for a curve with 133 points. And sometimes you have two numbers, like for genus 5, you have a 40 and a 44, which means that the best upper bound is 44, but what we know how to construct, or we know how to prove the existence, is that there is a genus 5 curve with 40 points. And you can even click on these numbers, and it tells you who have found the value and how it was found, and the same for the upper bound, how you could obtain it. I mean, there are techniques for that we will speak about probably in the second part of the course. All right, so let's come to the case of interest for us. So we are over F47, and we are looking for genus 5 curve. And you see that indeed, in genus 5, the best upper bound is 113. So that's the target we have. But right now, people know how to construct a curve of genus 5 over F47 with 108 points. And it is even given explicitly like this. So indeed, we can see that the value, this is an open question for us.
Okay, so this proves that this question is still open now. So let's see point B. Are more people interested? And the answer is yes. I mean, this is a big topic in mathematics. I mean, as every big topic, it starts with Gauss. So Gauss, in 1801, in his famous Disquisitiones Mathematicae, so in the section 358, says that he wanted to count the number of solutions of the equation x cubed plus y cubed plus z cubed congruent to 0 modulo a prime p. So, I mean, if we are reformulated in the terms of finite fields, I mean, as you will see, I mean, this is really counting the number of rational points on a curve over Fp. Closer from us, I mean, in 1985, Serre, Jean-Pierre Serre, gave a series of lectures at Harvard University. I mean, these lectures were really famous, and in particular, in this lecture, he solves the question of what is the maximal number of rational points for a genus 2 curve over any finite field. Okay. So, I mean, this gives you also a bit, maybe a measure of the complexity of the problem, because, I mean, Serre did the case of genus 2. So, I mean, you can imagine. And so these lectures at Harvard, I mean, now, I mean, they are going to be published this year. So, I mean, you can even, like, have a proper copy of these lectures. And, like, just to conclude, this year, in 2021, there will be an international conference precisely on this topic, where, I mean, in particular, we are going to celebrate the release of these notes by Serre. So yes, I mean, this shows you that there is a community that is really interested in this problem. The other thing is that, I mean, there are plenty of interaction with other topics. I mean, when you study these topics, then, I mean, you can have interactions with something which is called error correcting codes. I mean, error correcting codes, I mean, they are the codes that help you to correct errors, because each time that you try to communicate something across a channel, whatever, I mean, an electronic one, the voice, any kind of support, then you have errors that are introduced in the communication, and you want to correct them. And you want to correct them in the best way possible. And, well, I mean, that's the big and the nice surprise with mathematics, is that curves over finite fields, they play a role in this very applied area. Another very applied area is, of course, cryptography. And here also, there is a big connection with curves over finite fields, which are used in cryptography to design very efficient crypto protocols. And more recently, people have found very nice relation also with combinatorics. So yeah, I mean, there are plenty of interest around for this topic. Point C. Are you going to learn any interesting stuff meanwhile? Well, I think that if you have looked a bit at the program of these three series of lectures, then you see that we are going to study a lot of different mathematics. And I think, I mean, for me, that's really what brought me to this topic, because you never get bored. Each time you study like a different kind of math. It can be complex analysis, it can be number theory of a number field, algebraic geometry, and so on and so on. So there will be plenty of things to study. And I'm just trying to give you like a rough idea on how the different parts of the three courses are going to be related. So let's see, I mean, if I can, no, I think I have to switch over there because I will need a full blackboard to explain that. So, as a first piece, you have algebraic geometry. I mean, yeah, this is already huge, because somehow here, all like classical algebra of polynomials and geometry is related. So you have already like a huge topic which can go very, very far away. And the nice thing is that we are going, of course, to use only a tiny part of it, which are the geometry of curves. So here, what is going to be the first part of my course is to explain you the geometry of curves of low genius, how to describe them. And up to genius 5, so we will be able to describe what are curves of genius 5. So this is going to be my first part. Then you have another box here, which is Marseglia, Stefano's first part. So Stefano is going to do number fields. And in particular, orders in number fields, and also lattices or like modules over these orders. So this is another kind of things. Here we have like more like number fields, so fields of characteristic 0, when here our curves are going to be over fields of characteristic p. So there are two different worlds. But at the same time, in these two worlds, you have one object of common interest, which is called the Picard group. So the Picard group, it's a group, and it plays a role in the number fields, and it's going to play an important role here, and in particular its degree 0 part, which is called the Jacobian of the curve. And in order to describe this comes Anna Somoza part. So Anna is going to help you understand these objects, these Jacobians of curves, and more generally what are called abelian varieties. But unlike curves, even to get equations of these objects is in general very hard. And so the thing is that, I mean, it's a much complicated object because curves are dimension 1 object, when here is going to be a dimension G object, so it can be as big as you want. So in order to study them, I mean, and to really try to get some intuition, the idea is to look at them only over the complex. And you may say it's weird because here I want to study finite fields, here I'm going to be over the complex, here I have number fields. So what is the relation between all of this? But this is really going to be the beauty of it. And so the first thing is to start with elliptic curves, of course. I mean, Anna is going to recall or maybe teach you how it works for elliptic curves over C. And then we will move to more general lattices. Well, or torus of larger dimension. And one nice tool to understand all these objects are going to be some analytic functions, which are called theta functions. All right, so classical arithmetic of a number field, algebraic geometry, and analytic geometry. So already here you have like a broad topic. But now this gives you the, let's say, the geometric situation. Now we need the second part of the course. As I say, I mean, this second part is going to be released a bit later. So from the geometric situation, we need to move to the arithmetic. Arithmetic of curves over finite fields. And in particular, one important theorem that we are going to study, of course, are the Weil conjectures for curves and their consequences for the maximal number of rational points so over finite field. And now, I mean, so you have curves over finite fields. And, well, so that's really going to be our topic. But it means that now I have really lived from curves that could be like on any given field, in particular subfield of C, where this way to look at them or to look at the Jacobians would make sense, to a topic where I'm going to be over finite fields. So this means that I need to understand this over arbitrary field and in particular number field. So there is going to be a second part here, which is going to be so geometry and arithmetic of abelian varieties over finite field. And here, I mean, this topic is going to be more difficult in the sense that you will need like a deeper intuition of how it works, and a deeper knowledge of algebraic geometry. But thanks to the different pieces that we build, in particular the piece over C, even if you don't know all these very difficult results of algebraic geometry that would be necessary to prove all the theorems. You will get enough intuitions to go along, okay? And to go along until where? Until the last topic here. So, which is going to be part 2 of Stefano. And what is this part 2? Is to establish a correspondence between this object, I'm going to call this, and let's say, and this object. And that's really the beauty of it, is that you will be able to understand some classes of abelian varieties over finite fields in terms of certain modules over orders in number fields. And this is really nice because, as I said, these objects are already hard to describe. This one, you can imagine they are even harder somehow. But thanks to this correspondence, then you will be able to really give like a precise description that will, which you will be able to really play. And I think that one of the common features of all we are going to develop is the following, is that you really want as maximum, so let's put it like this, be explicit and effective. Right? We don't really just want to say it exists. We want as maximum as possible to be able to play with these objects. And in particular, I mean, when the genus is going to start to be bigger and the finite field is going to be also big, then you can't do it by hand. If you really want to play with these objects, it means that you're able to do it with computers. And so one part probably is going at some point to be able to learn some computational software. Okay, so that's the overview of the program, and I think, I mean, I hope at least it convinced you that you will learn a lot of material if you follow the full course with us. And even if you grab only a part of it, then it's already going to be a very nice introduction to any of the topics you have on the blackboard. So what remains now is point D. Are we going to solve it? Can we solve this problem of is there a curve of genus 5 over F47 with 113 points? Well, if I would say yes, then I mean I would have done it. Okay, and I would have already published an article. So the answer is, I don't know. I guess, I mean, from all you're going to learn here, it will make you able first to appreciate the difficulty of the problem, to really sense that, yeah, okay, I understand why nobody has solved it, and I understand maybe why it could be solved, because we are going to give you, with all this, some tools to address the problem. But now, to say that we are going to solve it directly, it's not clear. Maybe we are lucky, and yes, at the end of this course, someone gets a very nice idea and it can be solved. Most probably, it will mean that you're at the start of getting a very nice subject for, let's say, a full PhD. I mean, maybe that's really, if that should like tell you the amount of work and the goal at the end, that could be it. I mean, it could be a very nice PhD topic. All right, well, thanks for listening to this introduction, and we shall start for the courses now.